Welcome to Lecture 3. In this lecture, we'll look through EEPROM, or Electrically Erasable Programmable Read-Only Memory. We'll go through capture and compare modes, and the pulse width modulation, or PWM. EEPROM, or Electrically Erasable Programmable Read-Only Memory, is very common in electronic systems. It usually comes in a small chip or a small component, and it's a form of non-volatile storage. So non-volatile storage is storage where data is not erased when it's powered off, whilst volatile storage is temporary data memory, which can only be activated when it's powered on. EEPROMs are usually integrated in most microcontrollers since they require some form of memory. And flash memory, which you might be familiar with the name, derives from the EEPROM. So generally, EEPROM are used to store parameters or the firmware of a system in that way that it's permanent and doesn't require reprogramming every single time that you run a different set of code. Now, something to note here is that EEPROM can even store whole programs. In that way, the EEPROM gets loaded straight away when you power it up, and thus you don't need your microcontroller to be connected to your device. EEPROMs have their own language, much like your microcontroller's low-level assembly or assembler language. And different EEPROM modules will have their different capabilities, but most of EEPROMs will have these capabilities, which is how to enable writing, disable writing, and reading the data and writing the data. So something worth thinking about is the switch that you see on your SD cards. They sort of enable or disable writing off that SD card itself. And generally, EEPROMs has a life cycle of a million rewrites, which means you can rewrite the data inside the EEPROMs millions of times before they go out of life. As we mentioned before, flash memory is derived from EEPROMs, and the big difference is flash memory allows the use of NAND gates and NOR logic gates, whilst EEPROMs only use AND and ORs. So capture and compare mode allows your microcontrollers to capture input signals and or compare signals using your timer modules. They're regularly used to potentially synchronize with external systems or used to deal with time-based events. And generally, they're used in conjunction with timer module to provide some insight into time-based events. So something worth noting is that not all AVRs or not all microcontrollers will have both a capture and compare mode, or one or the other. Generally, they'll have one or the other, or they'll have none, depending on which AVR or which microcontroller you use. Do note that there are other microcontroller units which have both capabilities of capture and compare mode. So check your data sheet for more information about the possibility of using capture and compare modes. So looking at capture mode captures a signal from a particular pin. It encodes the time at which a signal is received by your AVR and can be set to capture rising edges or falling edges. Again, this capability depends on the microcontroller you use, so you should refer to the data sheet to ascertain what capabilities your capture mode has. So generally, the capture pin can trigger an interrupt based on a rising edge or a falling edge. And again, that depends on the microcontroller you're using, and check your data sheet to set that up. So let's look at an example of where capture mode can be used. Imagine you have a production line and it's a fast-moving conveyor belt transferring boxes of varying lengths from one place to another. How do you determine the length of the boxes? And you have a laser sensor which triggers a high signal when an object is in between the emitter and receiver. So as your box goes through it, the laser sensor will trigger a high signal until the box disappears, and then it will then go back to a low signal. So before we start using a specific module for an application, you really need to have a think about the application itself. So firstly, you need to see what information do you need from the application to warrant the use of capture mode, for example. Secondly, you need to think about what exactly you need to capture with your AVR or your microcontroller. Again, your datasheet will tell you what the capture mode will provide you, giving you an option of what's out there and what information you can use to perform your task. So let's stop a few seconds here to look at the previous example. So quickly have a think about this and bring that into the interactive session, and we can have a short discussion about what to do with capture mode. Okay, so if you haven't done it, I hope you go back and attempt to come up with a flowchart to see how you would achieve the example from the previous slide. So something worth noticing when you're using capture mode is how does it relate to your timers and how you can use that information. Another aspect you should look at is resource utilization. So depending on the microcontroller or the AVR that you're using, the resources available are limited. So microcontrollers and AVRs are very powerful, but one of the cons is that they are limited in resources. So using your resources effectively is key to a good program. Compare mode usually compares one register to another, and they are generally related to the timer modules. So generally you would have a microcontroller which uses a compare mode to compare, for example, the current time with a specific register, which then triggers something else. So as I said, performs an action when two relevant registers match. So let's look at an example of where compare mode might come in. So when given the previous example of your high-speed conveyor belt trying to track the length of the boxes. So when the length of the boxes are too long, a signal is sent from your system with a width of 50 microseconds to an external system. So the question becomes, how do you determine the 50 microseconds? So think about how many clock cycles is that? So what information do you need to obtain how many clock cycles 50 microseconds will take? Secondly, it generally relates to the timer modules. So how do you set your timer modules so that you can perform the comparison itself? So as we mentioned before, let's look at the example. So if the box length is too long, your system needs to set a hard warning to an emergency stop system, which is an external system, since it will break your production line. So to trigger the e-stop system, you need to send a pulse at 50 Hertz, so that's 50 times per second, with a signal width of 1 millisecond. So have a think about what you would do. So potentially, once again, have a flowchart of what needs to go through to achieve this. And also consider using the datasheet of your AVR or your microcontroller unit so that you know what resources are available and what registers you need to use to achieve this and how they interact with each other. And a big part of using your microcontroller units or your AVRs is the integration. So something worth thinking about is, so you need to send a pulse at 50 Hertz. So what is the pulse period? So how long do the pulses occur? How do you reset the capture and compare mode separately? So remember, you need to send a pulse with a signal width of 1 millisecond at 50 Hertz. So how would you set it up? What resources would you need to achieve this? So talking about resources, so once you've set up the capture mode and the compare mode, can you run another timer after setting this up? So this will be dependent on the microcontroller you're using, so refer to your datasheet as an exercise to see whether to answer these questions.